So in this video, what I would like you to do is to calculate this integral here. You notice this factor of 3 plus 4x squared to the power of 5 halves in the bottom. That, I hope, tells you how to do it. So try it, and a detailed solution follows on the next couple of slides. See you in a minute. Welcome back. Let's look at the solution on the next slide. So here is the integral that we want to calculate, and what I hope you've noticed is that in this square root, which is then raised to the power of 5, we have the sum of two terms, a constant and something times x squared, and that tells us it's going to be a tangent substitution. And if there was one power of x in the numerator, you could just write it down by inspection, but it's 2 powers of x. Now, one thing that you might think about is, well, you could always multiply top and bottom by a factor of 4, so you'd have a quarter, and then here 4x squared, and then in the numerator you could add and subtract 3, so you'd have 3 plus 4x squared minus 3, and that way you'd have two integrals, but they're not becoming totally trivial either, so I don't think it's worth trying to do that, but it's perhaps worth thinking about. Okay, so this term here has to be the side of a triangle if our substitution is to make sense. And because it's the sum of two terms, you know from Pythagoras' theorem that's going to work if this is the hypotenuse. So if this is a tangent substitution, the square root of this, in other words 2x, is going to be one side, and the square root of the 3, so root 3, is going to be the other side. And we should always pause at this stage mentally and just think, if I square that, I get 3, square that, I get 4x squared, 3 plus 4x squared, yes, that's exactly the square of this. So this does satisfy Pythagoras' theorem. Okay, so let's now make our tangent substitution. So the tangent of theta from the triangle is 2x over root 3, opposite over adjacent. And in case we need it, we can always immediately say from that theta is the arctangent of 2x over root 3. We can rearrange this, multiply both sides by root 3, divide both sides by 2, and we get that x is root 3 over 2 times the tangent of theta. And we're going to need the derivative of x with respect to theta, and we can write that down immediately because the derivative of tangent is sec squared and the constant just sits there. We could work out using algebra what the cosine of this angle is, but we can also read it off from the triangle. The cosine of theta is the adjacent over the hypotenuse, it's root 3 over the square root. And that tells us that 1 over the square root is the cosine divided by root 3. Okay, we now recall the function that or the relation that we're going to use, that the integral of f of x with respect to x is the integral of f of x rewritten in terms of a new variable, and then we insert by hand dx d theta, and then we integrate with respect to theta. So let's do that concretely for this integral here. We have x squared in the numerator. X is root 3 over 2 times tan theta. X squared is therefore going to be 3 over 4 times tan squared theta. I've written that here. This is multiplied by 1 over this square root to the 5 halves. Now, 1 over the square root to the power of 5. Now, 1 over the square root is the cosine of theta over root 3. So therefore, this to the power of 5 is going to be cosine of theta to the power of 5 divided by root 3 to the power of 5. So that's root 3 to the 4th times root 3. And root 3 to the 4th is 3 squared, it's 9. So this is 1 over the square root to the power of 5. And then we insert by hand dx d theta, and we got that ready earlier. It's root 3 over 2 sec squared theta. So we look at this and we see various nice things. So the root 3 factors cancel immediately, makes life look a little bit nicer. And the 3 here and the 9 partly cancel, leaving us with a 1 over 3 on the bottom. So looking just at the constants, we have 4 times 3 times 2 in the denominator, and that gives us 4 sixths, which is 1 over 24. So I'll take that outside of the integral on the next line. So now here we've got tangents, cosines and secants multiplying each other. To make sense of that, what I'm going to do is I'm going to write the tangent squared as sine squared over cos squared. So we have a factor of sine squared. There's no other signs here. And then we have a 1 over cos squared on the bottom. 1 over cos squared times cos to the 5th is going to cancel partly to leave us with cos cubed. Sec squared again means 1 over cos squared. So we've got cos cubed divided by 2 powers of the cosine. We're left with 1 power of the cosine. So that is our integral in terms of our lovely new variable theta. And this integral is one that we can perform by inspection. You just look at it and you say, oh, this is the derivative of sine. So if I had something like sine cubed and I differentiated it, I would get 3 sine squared of theta multiplied by the derivative of sine, which is cosine. So I would get 3 times that integrand. And all that's telling us is that the integral is going to be 1/3 of sine cubed theta. So we need those numbers. And now we can write down the sine. Again, you could use algebra, but you can read it off from the triangle. Sine of theta is the opposite over the hypotenuse. It's 2x over the square root. This is sine cubed, so it's 2x cubed, all cubed, divided by our hypotenuse cubed, so it's the square root cubed. When we expand that, we're going to get 8x cubed. The 8 and the 24 will partly cancel. So let me just do that. I'll get rid of the 2 here. That would give us an 8. This would partly cancel, and it would leave us with a factor of 3. So outside here, we have 3 times 3. That's 1 over 9. Then we have x cubed, and here it's the square root all cubed. And that is our answer for this integral. So, the point of this video exercise has been to give you some practice with a tangent substitution where it's not just something like x squared over 1 plus x squared. There are some other numbers put in. And I think the easiest way to read off how to do this is just to say, well, I'll draw a triangle. This square root has got to be the hypotenuse, and that tells us just from looking at it, if I want x to be essentially the tangent of theta, I take the square root of this, 2x in this case, and the square root of this, root 3, and then the tangent of theta is 2x over root 3. And then we perform the substitution and hope the integral becomes easy. And here it was just a matter of tidying up the algebra, and then we recognise here that this is actually an integral that you can perform by inspection. And then we transfer back into our original variable, unless it was a definite integral, which here it isn't. And to do that, it's easiest again, I think, just to use the triangle. So on the next slide, I'm going to give you a couple of exercises. So the first exercise is to differentiate our result for the integral and show that you obtain the initial integrand. And the way I would always do this is I would take the 1 over 9 outside, I would say here we've got x cubed multiplied by this to the power of minus 3/2. So I'm using the product rule and the chain rule. You'll get two terms, you put them together on a common denominator, and this will drop out. Secondly, an integral similar to the one that we've just completed, the integral of 1 over 4 plus 3x squared. I've swapped the 4 and the 3 around to the power now of 3/2, and this is the answer that you should obtain. And so demonstrate it by integration, and of course you're very welcome at the end to differentiate this and show that you obtain the original integrand. With that, I'll stop this video.